That was the Bach Prelude in C major from his Well-Tempered Clavier, book number 1. It's a relatively famous piece. A lot of students learn to play it just in the first few years of learning to play the piano. But it's a particularly special piece to me. That's why I played it for you this afternoon. It first sparked my interest in neuroscience and music, more specifically the interlap or overlap between the two. When I was 15 years old, I was a music volunteer at a hospice home. And my very first day, I walk into their facility and I sit down at an old and dusty upright piano in the corner of the common room. There's some people, some patients sitting on the couch. There's some standing in the hallway. And there's a woman to my right sitting in a chair, kind of slouched over with her eyes closed. Her arms are kind of in, hugging herself, it looks like. I thought she was asleep. But, so I'm playing this, old piano, and one of the pieces I was playing was a Chopin nocturne. And as I was finishing this piece, I started to play, I said, I want to play the Bach Prelude next. And when I did, something remarkable happened. As soon as I started to play, that woman in the chair kind of opened her eyes. She raised up a little bit and started waving her arms a little bit and even started humming along. Right? So she was humming along with this song, and I didn't really think much about it until one of the home nurses came up to me and said, after I had finished that piece, that that woman in the chair hadn't vocalized or made eye contact with anybody in months. Now, this was a really, really special moment for me because it introduced me to the power of, or potential of, music as medicine. It went, the moment went a little something like this.
We first see Henry inert, maybe depressed, unresponsive, and almost unalive.
Henry.
Yeah.
Henry.
Yes, sir.
I found your music. You want your music now?
What's up to you?
Okay. Let's try your music, okay? And then you tell me if it's too loud or not.
Then he is given an iPod containing, we know, his favorite music. And immediately he lights up. His face assumes expression, his eyes open wide. He starts to sing and to rock and to move his arms, and he's being animated by the music.
And he used to always sit on the unit with his head like this. He didn't really talk to much people. And then when I introduced the music to him, this is his reaction ever since.
So I'm interested in what happened to the patient in the hospice home when I was 15, and I'm interested in what happened with Henry here. More particularly, I'm interested in why it happened. I want to answer, or at least start to answer the question, why does music have such a unique ability to animate and seemingly alleviate the symptoms of some of these patients, even if just for a few moments? Now, I've spent a lot of time researching, and I'd love to share my ideas with you today, but before we dive any deeper, let's cover some scientific fundamentals. This is the human brain. It is extremely complex. It's composed of 86 billion neurons, which make up over 100 trillion synapses, which are the connections in between neurons. Now, there are other complex organs in the body, but the brain is unique. The digestive system, for example, it's a complicated group of organs where if one part fails to work, the entire system shuts down. But this is not the case with the brain. When one part of the brain fails, neurons from other parts can actually compensate for their neighbor's inadequacy or loss in function, and the organ as a whole stays viable. This adaptability is what neuroscientists call plasticity. Now, the brain is complex and plastic. It's also relatively segmented, both in anatomy and function. For example, we have the four lobes here. I'll use this one. So we have the four lobes here. The frontal lobe is where emotional processing is taking place. We have the parietal lobe in the middle on the top here. This is where the somatosensory cortex lies, which is where sensation information is processed. In the back, we have the occipital lobe. Of course, this is where visual information is processed. And then finally, we have the temporal lobe here in green. This is where the primary auditory cortex lies, and this is an area of the brain that we're going to be talking a lot about for the rest of this presentation. Now, those neurons I mentioned earlier, the 86 billion neurons that are in this brain, they're the fundamental and functional unit of this organ. They're highly specialized cells, and this specialization is what allows for this plasticity to occur. So let's take a look at the neuron a little bit more in depth. So, as I mentioned, it's the functional and fundamental unit of the brain. It's composed of three main parts. We have the soma, which is the cell body, which is this area right here. We have the axon, which is used to send signals from the soma to other neurons. And we have the dendrites, which are used to receive signals from neighboring neurons and then send its own signal through the axon, and so on and so on. Now, the axons here, you can see that they're covered in something called myelin, that yellow substance. Now, this is a fatty substance that helps signals travel faster. Neurons with myelin are called white matter, and neurons without myelin are called gray matter. Now, this neuron is also extremely plastic. So the brain as a whole was adaptable and plastic, but the neuron at the cellular level is the driving force behind this. In current neuroscience, it's thought to be the mechanism behind learning, memory, and essentially most of the unique characteristics that make the brain such an important and special organ. So if plasticity is so important, let's take a look at a general schematic of how that works. There's many different forms of plasticity, but for our purposes, we're focused on what is called Hebbian plasticity, named after the late scientist Donald Hebb. Now, it can be summarized as such. We have a system of neurons that make synaptic connections between, so we have neuron A, we have neuron B, and we have neuron C, and they make synaptic connections here from A to C and B to C as well. Now, these neurons can be in different parts of the brain. They can be in charge of doing different things, but Hebb's law states that any two cells that are repeatedly active at the same time will tend to become associated with each other, so that activity in one facilitates activity in the other. So, as an example, if neuron A is stimulated, that signal travels down the axon and sends a signal down to be received by the dendrites of neuron C. Now, this simultaneous action of neurons A and C is going to result in Hebbian plasticity and a strengthening of the synaptic connection between neurons A and C. Whereas if B is not stimulated, then essentially we have no increase in synaptic strength and there's no plasticity occurring here. Now, don't get too caught in the weeds here. It's a very, very complicated process, especially if you dive deeper into the molecules and proteins of it all. But essentially, activation of one neuron can not only change the activation of another, but also the strength of the other neuron itself. There's a well-known saying or quip in neuroscience that summarizes this effect in a witty way. It's stated, neurons that fire together, wire together. So now that we've covered some fundamentals of neuroscience, let's move on to how those neurons process sound and ultimately create the sensation of what we call music. So when I do this, the piano string is vibrating air at the speed of sound that travels to each and every one of your ear canals. Now, those pressure differentials travel down your ear canal and stimulate your eardrum. Your eardrum then in turn stimulates the cochlea. Now, the cochlea is an extremely important part of this process because the cochlea is in charge of translating the mechanical vibrations from in the air into an electrical stimulation that then can be understood and received by neurons. So if the cochlea translates mechanical vibrations into electrical signals, then it makes sense that we're going to have neurons that follow in this cascade. And indeed we do. After the cochlea, that signal, that electrical signal now, is received by the auditory nerve. The auditory nerve then sends it all the way down through the brainstem, through the thalamus, and finally to the primary auditory cortex. Now, the primary auditory cortex, I'm going to say that a lot, so here and after we're just going to say PAC. But it's a very important part of the brain. This is essentially the region of the brain that creates the sensation of music, right? It's not just an electrical signal. It's not just a pressure differential in the air. It's music, right? When you hear this chord, that being music to you is your PAC at work. Now, if that's not complex enough or beautiful enough, it doesn't end there. After the PAC, there are many areas of the brain that receive signals. The primary auditory cortex has tracts that go to many other areas of the brain, including, but not limited to, the basal ganglia, the frontal lobe, and the hippocampus. Now, these tracts after the PAC are extremely important in our perception of music as a whole. It's the reason, the connections to motor areas of the brain is the reason why you might want to tap your foot or nod your head when you hear this. Right? You want to move a little bit. Connections after the PAC to other areas of the brain are exactly why. The connections from the PAC to the hippocampus is also a very, very well-known, well-established connection. And the hippocampus is the memory center of the brain. But the connection from the PAC to the hippocampus is also extremely important. It's the reason why this means absolutely nothing, but this does, right? So we remember that. The connections from the PAC to the hippocampus, the memory center of the brain, are precisely why we remember certain musical melodies, why we remember something as songs. We associate that with Happy Birthday to You. Those words pop in your head as you're just hearing these electrical signals or hearing these pressure differentials, right? So it's an extremely important part of sound processing, these connections after the PAC to other areas of the brain. So we've talked a lot about how the brain operates under normal conditions, or how it's expected to work. Now let's take a look at the brain when it doesn't work as intended. Neurodegenerative diseases are a very serious and common reason why the brain might not work as it should. They are, by definition, characterized by neuron death, and they can lead to many different symptoms, depending on the specific disease that is causing those symptoms. Some of the most common neurodegenerative diseases include Alzheimer's, Parkinson's, ALS, and Huntington's. Now, there's a reason why these diseases, although they're all neurodegenerative, cause different symptoms. It's because the neuron death caused by each of these individual diseases is not in the same area or not targeting the same type of neuron, right? So the type of neuron or the area of the brain that's targeted is going to be responsible for the types of symptoms that these patients are experiencing. And indeed, in neurodegenerative diseases, usually certain specific areas are targeted. And there's another important point to make here. To differentiate between, throughout the track of a neurodegenerative disease, differentiate between a compromised area of the brain and a dysfunctional area of the brain. When you start experiencing symptoms of a neurodegenerative disease, you might have compromised areas of the brain. This is where the function might still be possible under certain circumstances, but not all, and still not acting normally. But we can only call an area dysfunctional when under no circumstances does a certain area or a certain type of neuron act as expected. With this in mind, with this overview of neurodegenerative diseases, we can start to talk about them one by one. And one of the most common neurodegenerative diseases is Alzheimer's. Alzheimer's affects over 50 million people worldwide, including 7 million in the United States. Symptoms include memory loss, cognitive impairment, and personality changes. Physically, though, Alzheimer's is characterized by plaques and tangles that correlate with neuron death. So you can see here that we have in a normal situation, a system of 3 neurons, but we have plaques and tangles riddling both inside and outside of the neurons. And there's going to implicate the ability for neurons to communicate with each other, causing symptoms. Now, as I mentioned before, not all areas of the brain are affected similarly or at the same rate. Alzheimer's focuses its damage on the entorhinal cortex and the hippocampus, that memory center of the brain, that area of the brain that made those random notes sound like nothing, but happy birthday sound like something. Okay, how are we doing? Any questions? I would open the floor to any questions. If there's anything I can go over again, I'm okay with it being interactive, but if anybody has anything, if not, we're good to go. All right, awesome. So the figures, it's going to speed up, trust me. So the figures I'm about to show are from a study done in 2015 that wanted to answer the question, why can musical memory be preserved in advanced Alzheimer's disease? Why can some people with Alzheimer's remember the words to a pop song they learned when they were 15, but not the names of their own kids? This study looked at an anatomical region of interest associated with musical memory and overlapped it with 3 different markers for Alzheimer's disease: gray matter atrophy, hypometabolism, and those plaques that I was telling you about earlier. On the right here, you can see a heat map of sorts. It's kind of a key. And on the right is the key, on the left is the heat map of what we're marking for Alzheimer's, right? So in this specific figure, we're looking at gray matter atrophy. Gray matter, again, is just a type of neuron that has no myelin. And so gray matter atrophy is essentially marking the death of neurons without myelin. Again, on the right is this key, and this red vertical line that we see is the median score within the musical region of interest. So on the top, it's outlining in red the musical region of interest. And on the bottom, we can see it's kind of an Italy-shaped looking thing outlined in white, right? So that's going to be overlaid on top of the markers for Alzheimer's, in this instance, gray matter atrophy. What we see here is a relatively low median score for this marker, gray matter atrophy. We can see that just physically looking at the brain, these red, yellows, and oranges are virtually nowhere inside this musical memory region of interest. And like I said, they looked at 3 different markers. This is one, gray matter atrophy. The next is hypometabolism. Hypometabolism being just lowered speed or lowered amount of normal metabolic processes that happen in neurons. And we see the same thing here again. We have a median score of almost 0, right? This musical memory region of interest is largely left alone by this marker for Alzheimer's. And moving on to the third, which are the amyloid beta plaques that I was talking about earlier. When they quantify this, we see a higher median score for the musical memory region of interest, but we still see that relative to other areas of the brain, it's much less. We can see that almost the entire frontal lobe is covered in red and yellow, right? So we have high markers for amyloid plaques in the frontal lobe, and yet relatively low in this musical memory region of interest. This study summarized their findings with the following quote: "The regions normally involved in musical memory and coding are strikingly well preserved in Alzheimer's disease. They even went so far as to say that this may well underlie the observed preservation of musical memory in Alzheimer's disease, that this anatomical discrepancy might even be the reason why it exists in the first place." Okay, I'm going to check again for questions. We understand the findings of the study? Awesome, great, okay. So I told you that the primary auditory cortex was going to be a large focus of today's presentation. This is where we start talking about it and we never go back. So compared to this study, or complementary to this study, where musical memory regions of interest were found to not be targeted by Alzheimer's, I also found a separate study that autopsied the brains of Alzheimer's patients, and they found something very interesting. They found that the tangles and plaques that are characteristic of this disease were not heavily found in the primary auditory cortex, despite still finding them in surrounding areas. Right? Even though it was found surrounding the PAC itself was quote unquote virtually unaffected. Now, I don't think that this is a coincidence. I think that the fact that areas of the brain involved in music processing and the PAC itself are less compromised than others is actually the fundamental reason why music has the unique effect it does for Alzheimer's patients. And that's what the paper concluded. You know, it may well underlie this, but I'm going to take it a step further. So Alzheimer's disease is a really great example of what music therapy can do for patients with neurodegenerative diseases. We heard prominent neuroscientists say in the video that I showed you at the beginning of this presentation that despite severe memory problems, patients with Alzheimer's disease can remember music, and music can actually facilitate the recall of other episodic memories. Here we see a before and after of Henry listening to music, and I just think that this effect is absolutely amazing. So to summarize everything that we have talked about so far, we can create a chart and ask, for Alzheimer's disease, what is the area targeted / most affected? And we can answer entorhinal cortex and hippocampus. We can also ask, are there significant connections between that targeted area and the primary auditory cortex? And we can say yes. And finally ask, what is the efficacy of music and music therapy? And we can see my story with the at the hospice home, as well as this video with Henry, and quantifiable data and other studies that absolutely music therapy is efficacious for patients with Alzheimer's disease. Now, this brings me to my hypothesis. What I propose is that music uniquely affects individuals with certain neurodegenerative diseases because, due to the anatomical focuses of those diseases, the PAC can facilitate activation and plasticity, aiding in the function of the compromised areas. So essentially what I propose is happening in Henry's case is this. His brain is riddled with plaques and tangles, right? He has advanced Alzheimer's disease, and the neurons in his hippocampus are not acting as they should. But when he listens to music, this is what I propose. The primary auditory cortex activates, temporarily boosting his ability to converse, mitigate his symptoms, and even for a short while, even if just for a short while, through the use of Hebbian plasticity. And this is only made possible by the connections between the PAC and the hippocampus. Essentially, music is hijacking his brain to a greater extent than the disease is. Now, if this hypothesis were to be true, then the general schema of what I'm saying should follow with other neurodegenerative diseases. Are there other diseases that might behave in the same way? So let's take a look at Huntington's disease. It's much less common than Alzheimer's. Only about 40,000 are affected in the US compared to 7 million like Alzheimer's. It's also inherited. It's caused by a single gene mutation on chromosome 4, so it's genetic. And the area of focus for damage with this disease is different. It focuses on the basal ganglia, and we'll talk more about what that is and what that does. Symptoms include motor dysfunction, cognitive impairment, and psychiatric symptoms, amongst others. So let's take a look at the basal ganglia, this area of the brain that Huntington's disease targets so fiercely. As I mentioned, neurodegenerative diseases don't just target one area of the brain, don't just target the entire brain, they target usually one specific area of the brain or type of neurons. So this basal ganglia is a set of structures deep within the brain. It's composed of many structures, including the putamen, the substantia nigra, and the caudate, amongst many others. The basal ganglia is involved in movement control and smoothing out of those movements. So when I put my hand up to high five you, and you high five me, and our hands line up perfectly, that's your basal ganglia at work. Now, in Alzheimer's disease, we saw connections between the hippocampus and the primary auditory cortex. And remember, again, the hippocampus was the targeted area of Alzheimer's. And that might actually be the reason why music therapy is so effective for those patients. Let's ask, is this the same for Huntington's? And we see, yes, it is. The study quotes a strong structural connectivity between the primary auditory cortex and the putamen, which is a substructure of the basal ganglia. This leaves without a doubt that significant connections exist between the primary auditory cortex and the basal ganglia. So now that we've established that Huntington's has a specific area that's targeted and that the primary auditory cortex makes connections with that area, the next question is inevitably whether music is efficacious for Huntington's patients or not. Now, this study states that music therapy was beneficial for them. They also gave us an example of a case study. This is a 54-year-old male who, when was younger, was heavily involved in rock music. Now, the study said that listening to well-known music, which was rock music for him, visibly calmed him. It lowered involuntary movements, and those involuntary movements are characteristics of the disease. As I said, the basal ganglia is in charge of smoothing out those movements. So when that area is implicated, you're going to have a harder time. There's going to be some tremors. There's going to be some shakes. You're going to be less accurate with where you're moving. He was actually even able to play the guitar. And the study noted that being able to play the guitar was an extremely important improvement for him because, when you're not exactly able to make certain hand shapes, but you're able to do chord shapes with your hand, right? That's a really amazing improvement. So let's summarize what we've talked about regarding Huntington's disease so far and compare it with Alzheimer's. So we see that the area targeted is the basal ganglia. We can ask if there are significant connections between that target area, the basal ganglia, and the PAC. And for that, we can say yes. And we can ask about the efficacy of music and music therapy, of which we can say that it is well established. So if Alzheimer's and Huntington's both follow this schema, then potentially we can see the same thing in other neurodegenerative diseases and really establish a strong pattern. So let's explore Parkinson's. Almost 1 million are in the United States are affected. This neurodegenerative disease targets the substantia nigra, which is a sub-area of the basal ganglia. Now, there's a myriad of symptoms shown here, both motor and non-motor related, but let's take a look at this substantia nigra, this sub-area of the basal ganglia that the Parkinson's disease targets. It solely uses dopamine as a neurotransmitter, and as expected, it controls movement and coordination, and most importantly, receives input from the auditory cortex. Now, this is a 2003 study that researched the pathways issued from the auditory cortex involving the substantia nigra, which is the area targeted by Parkinson's. This study establishes without a doubt that these connections indeed do exist and allow the primary auditory cortex to influence the activity of the substantia nigra. Knowing that these connections exist, the next question again inevitably becomes whether music and/or music therapy is beneficial for Parkinson's patients. And we find that it certainly is. A systematic review done in 2021 looked at data from the previous 5 or 6 years and did a metasynthesis that concluded that music therapy improved both motor and non-motor symptoms in Parkinson's patients. Let's take a look at what's possible through music in a patient who experiences juvenile Parkinson's disease. What you're going to see in this video is an individual that has a hard time communicating, a hard time walking up stairs, a hard time walking with regular rhythm, but to do something extraordinary when he sits down at the piano.
My brother, he has autism and Parkinson's. He can't really speak that well.
He understands what I say to him, but he doesn't always respond.
It's really hard to walk for him. It's really hard for him to do much.
就想通过音乐来疏解他心里的这种情绪。
All right, Jason, you ready? Okay, we're gonna walk up to the stage area. All right? Do you need me to help you, or you're good? You good?
因为爸爸学过音乐一些东西，所以觉得能怎么样给他治病。
Once he starts playing, he's a different person, and he's able to completely calm down and relax and play through a song perfectly, having no shakes, no movement, no jerks.
So you heard what his teacher said, right? He becomes a different person when he sits down at the piano. He's able to play without any jerks, no shakes, and completely relaxed. So music obviously has this positive effect on his symptoms. So let's continue to build this comparison and summarize the information with our knowledge of Alzheimer's and Huntington's. We see that Parkinson's follows the same schema. The targeted area of Parkinson's is the substantia nigra, that there are indeed connections between the PAC and the substantia nigra. And again, music therapy and music is efficacious in alleviating some of the symptoms of these patients. All right, I'm going to check for questions one more time. Yes?
Yeah, I have a question. So, since Parkinson's is more about like motor skills sometimes, I was just wondering, like, when you say music therapy, does that involve like, does it include like listening and like actively performing it? And is actively performing better for say Parkinson's, and then listening maybe better for Alzheimer's since that's more memory? Like, is there correlations?
Sure. Yeah, absolutely. So there is a definite neural difference between just listening and playing, right? There's a passive versus an active involvement in this music, which is why, and you're right, so far I've been kind of joining music and or music therapy into kind of the same idea. Neurally, it's a little bit different, but in terms of this hypothesis, the activity in the primary auditory cortex itself is similar. So the PAC itself, whether you're listening to music or whether you're playing music, that activity is going to be very much similar, but the connections outside of that from after the PAC are going to be a little bit different. So absolutely, the motor involvement of playing the piano with muscle memory is going to be more beneficial for Parkinson's and Huntington's that are more movement associated. And exactly like you said, Alzheimer's, which is more of a memory thing, sometimes there's case studies out there in some of the studies I've read where you have a patient who, like I said, doesn't remember names of their family members, listens to a couple pieces of music, and then will turn around and say, oh, like Sharon, and then they'll remember, right? So it actually facilitates some memory. So absolutely, the areas of the brain are indeed influenced, or actually the effects of music and music therapy are indeed influenced. And that's kind of the job of a music therapist, is to tailor the activities for the patient to what most benefits them based on the disease that they have. Great question. Any others? Yeah.
Are these results of like the relationship between music therapy and the patient based off of songs that they already knew, or is it based off of songs that they generally find enjoyable, or is it music in general?
Yeah, so that's an important distinction being made currently in the field. As of now, the general consensus is that well-known music is going to be the most beneficial in all cases, whether it's just memory, whether it's movement. It's not just, I can't play Mozart if you've never listened to Mozart before and expect it to heal you, right? So for example, that the Huntington's patient who was the case study who was involved in like rock and roll music when he was a kid, rock and roll music was what helped him play the guitar and mitigate his symptoms a little bit. I assume that if we're playing other kinds of music, it's not going to be as beneficial. Yeah.
So does this mean that patients who had developed musical skills prior to developing their disease, does that assist in this process? Like if someone did not know how to play the piano, did not know how to play the guitar, would this be much more difficult for them?
Yeah, absolutely. It's the strength and the tracks involved that have already been learned that are activated, right? If those connections in the brain don't exist prior to this damage, then they can't be utilized to help alleviate the symptoms. So absolutely, yeah. Musicians like Tony Bennett has Alzheimer's. He was able to remember lots of lyrics, but music is going to be really helpful for him because he knows a lot of music, and music is something that's very, very well established in his brain. The connections regarding singing and memorizing lyrics and all that stuff is going to be very much stronger in his brain than someone who has never sung or never does music. So absolutely. All right. Great questions. So before I continue, I want to mention that I am a skeptic. I want to challenge hypotheses as much as they can be. So let's take a look at Creutzfeldt-Jakob disease. This is an extremely rare neurodegenerative disease caused by a misfolded protein. And these neurodegenerative diseases caused by misfolded proteins are called prion diseases. Now, that may sound a little weird. The most famous prion disease, you guys may have heard of it, is mad cow disease. That's going to be by far the most famous prion disease, but still extremely, extremely rare. Now, there are many symptoms involved in Creutzfeldt-Jakob disease, including memory loss, personality changes, and motor impairments. I want to make a point here. We've seen each of these symptoms before. We've seen memory loss and personality changes in Alzheimer's. We've seen motor impairments in Huntington's and Parkinson's. So what makes Creutzfeldt-Jakob unique? Well, what we haven't seen is this. Creutzfeldt-Jakob disease targets the entire cerebral cortex. However, in my research, I actually found that while the entire cortex is damaged and targeted by this prion disease, the auditory cortex is actually more affected than the areas surrounding it. It's marked with, quote unquote, a tremendous loss of neurons. This is unprecedented so far. With Alzheimer's disease, Huntington's, and Parkinson's, there was a specific type of neuron or an area of the brain that was far more affected than the others, and at least in early stages of the disease, were left alone. Here, we see the entire brain. All 4 lobes are the victim of this rare and debilitating disease. And in addition to the primary auditory cortex being more targeted than the area surrounding it, I also found that hyperacusis is one of the first symptoms of this disease. Now, hyperacusis is just a decreased tolerance to sound. And to me, This indicates that auditory processing is implicated or changed early on in the disease process. So now that we've established that this is a bit different than the other neurodegenerative diseases that we have discussed so far, and obviously the primary auditory cortex is going to be more compromised in this instance than in something like Alzheimer's, let's see if music therapy helps these patients. I searched for a long time, and I haven't been able to find a single instance of music therapy helping a patient with Creutzfeldt-Jakob disease. In fact, when you look up music therapy and the term Creutzfeldt-Jakob disease in the National Library of Medicine, searching over 20 million articles, no results are shown. And just so you see, this isn't me like editing anything. This is not the case for the others. When you look at music therapy in Huntington's, music therapy in Parkinson's, music therapy in Alzheimer's, over 1,000 articles come up, or 1,000 studies come up for each of these diseases. So if Creutzfeldt-Jakob is so unique, let's compare it with the other neurodegenerative diseases and discuss what we see. So in Creutzfeldt-Jakob, the entire cerebral cortex is targeted, but the primary auditory cortex itself is at least slightly more targeted than others. Significant connections between the primary auditory cortex and the primary auditory cortex is not applicable, right? Although the PAC makes connections to itself within, if all of it is targeted, it's not going to be able to facilitate plasticity on itself, if that makes sense. And as we've seen, music and/or music therapy is not efficacious for these patients, at least what we know so far. So let's push this hypothesis just a bit further and look into other neurodegenerative diseases and see if we come up with anything else. There are many others, but the three most common that we haven't talked about yet are ALS, spinal muscular atrophy, and multiple sclerosis. Let's take a look at each of these three very quickly, and we'll be done soon. ALS is also known as Lou Gehrig's disease on the bottom. It's also the disease that physicist Stephen Hawking died of. This disease targets motor neurons directly. Now, the primary auditory cortex does not make connections with motor neurons. There are some connections between the motor cortex and the PAC. However, it's extremely important to acknowledge that those connections are made from the motor cortex to the primary auditory cortex, not vice versa. And finally, there is no evidence for efficacious music-based therapy. In my research, there don't seem to be any studies that support any benefit or connection between music therapy and ALS, and we see similar results for spinal muscular atrophy. This is a disease that's similar to ALS in that it affects motor neurons. SMA, however, specifically affects lower motor neurons in the spinal cord. Again, the PAC does not make connections with these lower motor neurons. And as we expect, there is no literature on music-based therapy with spinal muscular atrophy, similar to Creutzfeldt-Jakob and ALS. Finally, let's talk about multiple sclerosis. This disease targets the myelin, which is, again, that fatty layer around the axons of neurons that helps signals travel faster, and as well cell bodies in the prefrontal cortex. Now, we know that the primary auditory cortex makes connections with the prefrontal cortex, so our expectations might be different than with ALS or spinal muscular atrophy. And indeed, those expectations would be correct. Studies show that music-based therapy helped in essentially every aspect of the disease. This study says that overall, studies consistently showed that music-based therapy was better than conventional therapy or no intervention with regard to gait parameters, fatigue level, fatigability, coordination, dexterity, balance, walking endurance, lower extremity functional strength, emotional status, and pain. This review concluded that music-based therapy is a safe and effective approach for clinical rehabilitation of multiple sclerosis patients that leads to positive results regarding both motor and non-motor functions. Now, when we compare these three neurodegenerative diseases that we just talked about, we see a similar pattern occur. With ALS, motor neurons are targeted. There are no significant connections between the PAC and those motor neurons, and music therapy is not efficacious. Similar story for SMA. Lower motor neurons are targeted. The PAC does not make connections with that targeted area, and music therapy is not efficacious. However, in multiple sclerosis, myelin and cell bodies in the prefrontal cortex are targeted. The primary auditory cortex does make connections with those areas, and as we saw just one slide ago, music-based therapy is extremely effective in almost every single symptom of multiple sclerosis. So we have a pattern. Let's put it all together, and I'll show you that based on the principle of plasticity, not only is a healthy primary auditory cortex required, but also if the primary auditory cortex can connect to damaged areas and facilitate the positive effects. This is our big summary chart. This is the grand chart. I made it myself. So we can essentially summarize the entire presentation by asking ourselves two questions. Number one, are there significant connections between the targeted area of any given disease and the PAC? Number two, is there an established efficacy of music and music-based therapy? And from the hundreds of studies I've looked at, the current literature today will speculate that music can help Alzheimer's patients because the primary auditory cortex is left alone by those disease processes. But that's not what I believe to be the entire picture. My hypothesis states that it has to do with the PAC's ability and the neuronal tracts that accompany it to hijack the areas that are targeted to improve symptoms via plasticity. If it was merely the fact that the PAC was left alone, then why is music-based therapy not effective for ALS or SMA patients? ALS and SMA leave the PAC alone, but we saw that music-based therapy is not efficacious for them. If there was evidence for effective music-based therapy to relieve symptoms of an ALS patient or an SMA patient, that would heavily suggest that my hypothesis is wrong. Now, I don't think that the fact that every checkmark on top is matched by a checkmark right below it, and that every X is matched by an X right below it, I don't think that that's a coincidence. So, I have a neuroanatomical hypothesis for why music has the unique effects that it does on the brain. Now, hypotheses are early in the scientific method. It's just step 3 of 6, and any experienced scientist will tell you that those first 3 steps happen way faster than the last 3. Hypotheses also need to be testable. I believe that one of the weaknesses of my hypothesis and other hypotheses regarding the overlap of neuroscience and music is the practical testability of them. There are ethical considerations in some perfect study designed to test this hypothesis. Hypothetically, we would want to test this theory by having a series of experiments with 200 people, 200 people with a certain neurodegenerative disease, 100 with no treatment, and 100 with solely music therapy or musical treatment. Now, because we have some treatments for these diseases, that is an extremely unethical study design. So that is at least one limitation to testing this hypothesis as fast or as efficiently as we can. Despite that, however, there are lots of benefits towards pursuing this, included but not limiting to the fact that music-based therapy is extremely cheap and non-invasive. It's easy to implement both practically and financially. And I have a couple of other considerations or thoughts regarding this hypothesis. I want to mention and acknowledge that just because there isn't documentation of a certain music therapy efficacy, for example, when I looked up Creutzfeldt-Jakob disease and music therapy, just because there aren't any studies done does not mean that it doesn't exist. I acknowledge that possibility. There are other factors, such as the fact that Creutzfeldt-Jakob is a rare disease, so there's lower amounts of patients to do research on, so I acknowledge this possibility. However, in my research, with no case studies and with no formal reviews showing any instance of music-based therapy being efficacious, I'm willing to take that data and use it to make this hypothesis and am willing to do a study that might prove me wrong. Now, again, like the question I answered earlier, there's a difference between playing and listening to music. Henry just listened to music, right? That first video I showed you, but the patient with juvenile Parkinson's disease was playing music, right? They're very different processes in the brain, but both involve the primary auditory cortex, and at least for these purposes, are relatively similar. There are lots of other people doing great work on the healing power of music, not just in neurodegenerative diseases. And so while there are lots of areas to improve upon, all that means to me is that there's lots of areas to pursue and make this field all the more exciting. I believe it's a very, very promising direction to give attention. In the fall of 2025, I'll be attending medical school, where I want to continue researching this and answer my question, do that next step of the scientific method, and test my hypothesis. Ultimately, as a physician and as a musician working in the healthcare field, I want to create a viable space for medicinal music. So I'll leave you with this thought, that music is not just an emotional experience, but a physical one. That music does not just have the ability to heal your soul, but also to heal your body. I urge you all on your way home today to listen to some of your favorite songs, to truly connect with the music and cherish the emotions that it evokes. Because perhaps one day, it might be the melody or the song that helps you or someone you love find a path out of illness and back into the vitality of their healthiest days. Thank you, and I'll open the floor to questions one last time.